Our next topic is confidence intervals. So this is going to combine what we've learned in sampling distributions and how you practiced z-tables. So remember from the sampling distributions, we were pretending we knew stuff about the population and we wanted to see, oh, we're going to take samples. What has to be true so that our statistic, our estimate for the parameter, is pretty close to what it really is exactly. So we did that, and you got a few conditions where when we take a sample, if these things are true, we can be within a range of accuracy of the original parameter, like the mean or the proportion. Today, we're going to flip that. So maybe we know stuff about the population, maybe we don't. Sometimes you do in real life, sometimes you don't. And we want to say, okay, I've taken a sample. For example, on my first picture here, I calculated the sample mean, so the statistic, and I want to give it a little cushion. So my statistic, my sample mean is here. I want to give it a little cushion on either side so that I'm 95% confident. This is my confidence level. I'm 95% confident that the real mean of the population, so mu, the parameter, I'm 95% confident if I figure out these two boundary values that the true, the actual, the exact mean is within this range somewhere. And that's the point of today. So this is going to be an interval estimation. Remember, we had a point estimation, interval estimation, which we're doing now for the next few days. And then later on, we're going to do hypothesis testing. You're going to do problems. I'm going to link you to some YouTube videos where you're going to see how they do certain problems. And then you're going to practice that by yourself. So today is all about means. Just some notation. You don't have to take notes on this. You can, but you're going to get pretty familiar with this. Confidence level, like I'm 95% confident that the true mean in this screenshot is in this range. So you somehow calculate your statistic, your sample mean. You want a margin of error. So margin of error is E. That's going to be Z alpha over 2. Now, watch this. So if I'm 95% confident, it's related to the area of the normal curve. I have 95% in here. Based on symmetry, the remaining 5% is split up in the two tails. So these are the tails. So 2.5% is here, 2.5% is here. That makes up 5% that's remaining. So we're going to flip the z-table backwards. We're going to use it differently, but the same z-table for these. And we want to find, well, what is this boundary value, basically, so that I end up with 0.025 of the areas here, and by symmetry also here. You're going to get comfortable with margin of error. In this case, it's Z alpha over 2. So all that is if alpha over 2 is 0.025, I want to find what's the z-score, what's that boundary value, so that this area is 0.025. This is the z-score, quote unquote. And remember, that's also like how many standard deviations I am away from my mean, in this case, which would be x bar. So how many standard deviations times the quote unquote standard deviation estimate of your sample. So this is going to be your width, your margin of error. It's going to be half of this guy. It's going to be blep. I'm going to subtract it, and I'm going to add it. I'm going to subtract it and add it to get this whole range. So that's something you're going to play with z-tables. The next thing, you're also going to learn how to use t-tables. Now let me come down here. T-tables, or t-distributions, they're like z-distributions or normal distributions, but they're for when you either have smaller sample sizes or you really don't know the true population standard deviation. So if you'll notice, they're shorter and squattier. They give more of a area in the tails. You'll notice the blue and whatever those colors are, blue and teal, whatever they are, there's bigger area. If you slice it here, there's bigger area in the tails. That means I have to give a little more leeway since I don't have a large sample or for whatever reason. So you're going to learn something about degrees of freedom, which relate to, well, not everything is independent that I've gotten. Some of the data that I've gotten is relying on something else. That's a big hand wavy thing, but you'll use it in your problems. The theory, basically, like I said, it has heavier tail, so it gives a little more grace to the process. Like, all right, more potential for quote unquote error, so I need bigger tails. What did I do? Yeah, so, but the t-table is basically the same thing. If you compare the two pictures, of course you can stop the video whenever. If you compare the two pictures, the margin of the significance level is the same, alpha over 2, but now I have a degrees of freedom. For these kinds of problems, it's always going to be one less than the sample size. And instead of sigma, the parameter, I only know the statistic, the sample standard deviation. But you'll go through some problems, you'll see the same. But I screenshotted this because it's the same idea. If I want a 90% confidence interval, really that just means 90% in the middle, and you got to figure out, because you're going to use the t-table, you got to figure out, well, how much area is left in the tails. What else did I do here? Yeah, so this is, if you can stop this, if you need to, you can see how that's used. So that's the bridge between what we've done so far with the sampling distributions and the z-tables, and that's the bridge to what we're doing now, confidence intervals. Like, well, I really want to know what the mean is of the population. And this says, excuse me, this says, well, I don't know the exact value because I just don't, but I can give you confidence interval, like within 95% confident, I know it's somewhere in this little range, and that's the point of the confidence intervals.